Anytime we are relating more than one set of data, we call that a relation. Some relations are functions and some aren't. We'll talk about when a relation is a function and when it's not later. But first, let's look at this problem and see what the two sets of data that we're relating are. So it says in the scoring system of some track meets, first place is worth 5 points. Second place is worth 3 points. Third place is worth 2 points, and fourth place is worth 1 point. So the two sets of data that we're relating to each other are places and points. And typically we have an independent variable and a dependent variable when we're relating two sets of data. So you have to kind of ask yourself which one depends more heavily on the other. Sometimes there's not a big difference between the two, and it doesn't matter which one you set up as which. But in this case, it makes more sense for the points to be the dependent variable because the number of points you earn is dependent upon what place you get. So place would be the independent variable and points would be the dependent variable. There are 4 different ways that we can model a relation and its data. So one is with ordered pairs. Ordered pairs is when we write our data like a point, where our independent variable is written first and our dependent second. So 1, 5, first place is 5 points. Second place is 3 points. Third place is 2 points. Fourth place is 1 point. We can do that in a table where we have place and points. And again, first is 5 points, second place 3 points, third place 2 points, fourth place 1 point. We could make a graph. All of these are positive, so I'm just going to draw the first quadrant where our independent variable is written along the x-axis and the dependent variable is written along the y-axis. And then first place, second place, third place, fourth place. We could keep going. So first place is worth 5 points. We can put that point up there. Second place is 3 points. Third place, 2 points. Fourth place, 1 point. But one question you have to ask yourself if you are going to create a graph is, do you need to connect the points or not? In this case, this is what's called a discrete set of data. It's discrete because we want to leave our points as they are. We don't want to connect them because there's no such thing as 1.5 place. So I wouldn't want a line that connects first place to second place because up here at 1.5 place, that doesn't make sense. There's no 1.25 place. There's no 1.1 place. So it doesn't make sense to connect the points in this case. That's how you can tell if a function or a relation is discrete or continuous. In a continuous function, we would connect the points. And then lastly, we have what's called a mapping diagram, where your independent variable is written in one set, your dependent variable options are written in the other. So for example, our places are 1, 2, 3, and 4. Our points options are 1, 2, 3, and 5, and then we map which one goes to what. So first place goes to 5 points, and so on and so forth. The second thing we talked about is how to tell the difference between something that's a relation and something that's a function. All functions are relations. Not all relations are functions. To know if it's a function or not, we have to ask ourselves, does every input have just one output? Every independent variable has to know what output it's going to. How we can tell that with graphs is by asking ourselves, let's get that pencil, asking ourselves, does it pass the vertical line test? Or in other words, if I drew a bunch of vertical lines on my graph, does it always just hit my function or my relation once? If there's no way to draw a vertical line that hits your relation more than once, then it is a function. So in the second picture, this does not pass the vertical line test. It hits twice. This vertical line hits the relation twice, or this this vertical line at 1 also hits the relation twice. So that would not be a function. When we're looking at a table, we're looking at the inputs, and we want to make sure that every input has just one output. So -2 has just one output, it's -4. -1 has just one output, it's -4. 0 has just one output, and so on and so forth. So this is considered a function. Same with mapping diagrams, you're looking at the inputs. -3 has just one output, 2. -1 has just one output, 2 has just one output, and 4 has just one output. That's a function. But in the second mapping diagram, it is not a function because 1 has 2 outputs. 1 is going to both -1 and 2. That's not a function. And then when we're looking at a discrete graph like this one, we can look at this and see that it would not pass the vertical line test right here, and possibly right here too. It looks like if you're 28 years old, there are 2 different options for your outputs, and every input can only have one output, so that would not be a function. When we are finding domain and range, if it is a discrete function, you're just listing the values that are part of each set. So domain, when we were talking about domain, is referring to all the inputs or the x values. The x values or the independent values. The range is referring to the outputs. So for this mapping diagram, we would do brackets. Brackets mean the set of. And so our domain is the set, or the numbers that are in the set of our domain include 1, 2, 5, and 6. I always write my set in numerical order. That's typically how you'll see it written. It's not technically wrong not to, but that's how I like to do it. The range includes -4, -1, and 0. Those are all of the possible outputs. When we're looking at a graph, we just have to think a little bit harder about it. So domain, again, your inputs or your x values. Domain measure is left to right. So I'm going to start all the way to the left, and my leftmost point is right here, and that's at -3. My next leftmost point is right here, and that's at -1. Then I have my next one at 1, and my last one over here at 3. So my domain has 4 values, just like there are 4 points on that graph. If I'm doing the range, I'm looking at my y values. I'm going up and down. So because I go in numerical order, I'm going to start down at the bottom. So my bottommost point is right here at -2. My next lowest point is here at 0. My next lowest point is here at 2. And my topmost point is up here at 4. The next one is a continuous graph. It's continuous because my points are connected. There are infinitely many points on that segment, and because there are infinitely many points on that segment, we can't just list numbers for the domain. There are infinitely many numbers a part of that domain. So instead, we would write our answer as either an inequality, or we could write our domain in interval notation. Let's start with the inequality. My domain are my x values, which are left to right. So if we're starting all the way at the left, that's going to bother me. My leftmost point is right here at -2. So all of my x's are bigger or equal to -2. Equal to because it's a closed circle right there. And all the way to the right, I have a point here at 3. So all of my x values need to be less than or equal to 3. That's one way to write our domain in inequality notation. And interval notation, that would say all the numbers from -2 to 3, including -2 and 3. For my range, we're going to do something similar, but we're looking up and down, starting with the bottom. So my lowest point is down here at -1. Now we're talking about the y value, so I'm going to put a y. Y can be everything from -1 until 2. 2 is the highest point. And so in interval notation, that would say -1 through 2. Any of those values could be included. And again, we have to do this anytime we have a continuous graph because there are infinitely many points between the two endpoints. We cannot list them all. And this is a function that passes the vertical line test. The next set, we don't know that this is continuous, so we just assume that it's discrete. For our domain, we're going to list all of the x values, all the inputs. I'm listing them in numerical order. And for the range, we're going to list all of the outputs, the y values. And in numerical order, that would be 1, 2, and 9. That is a discrete set of data, and it is a function because every input had just one output. All right, let's do a few graphs that are a little bit trickier. So this first graph up here, domain, we're just going to list all the x values that are included. So there's a point right here at 1. There's a point over 2 points at 2. So this is not a function. There's a point at 4 and 2 points at 5. For my range, I'm looking at my y values now. So I'm going to start at the bottom. There's a point down here at 0. There's 2 points here at 1. Point at 2, and 2 points up here at 5. And I'm listing my points. I'm not writing an inequality or interval notation because it's not a continuous graph. So we only want those numbers to be included. The one underneath that, my domain includes, we have one all the way to the left is at 0, 1, 2, 3, 4, and 5. Even though it includes every number from 0 to 5, we would not write that as an inequality because we're not actually including every number between 0 and 5 because 1/2 is not included or 3/4 is not included. So when it's discrete, you have to just list them. Range is really easy on this one. All of those are at 3. That's how tall they all are. Or their location vertically is all at 3. Now the circle is a continuous function, so we either need to write it as an inequality, the domain, or in interval notation. So domain goes left to right. So on the left, it starts all the way over here at 0. And the furthest point over here to the right is at 6. So in interval notation, that would be 0 to 6. My range, so now if we're looking at top to bottom or bottom to top, the lowest point is down here at 0, and my highest point is up here at 6. So my range would also be 0 to 6, including 0 and 6. The next graph has a starting point right here, and it goes on forever. We haven't done one that goes on forever. A continuous graph means we need to write an inequality. So my domain, I'm reading left to right. My first point is here at 0. But then it goes on and on and on forever. So we're going from 0 to infinity, or we could write that as all of my x values are bigger than or equal to 0. My range, how tall it is, my lowest point is at 1. I shouldn't say tall. That's not really quite right. And everything else is above the 1. So y is greater than or equal to 1, or in interval notation, that would be 1 through infinity. Next one, my domain is all real numbers. We can just write it like this, fancy R, or in interval notation, that's everything from -infinity to +infinity. Every number is included. The arrow points to the left forever and to the right forever. My range is not all real numbers though, because there is a bottommost point. This function, it's the function, because it passes the vertical line test, never goes below 0. So my y values are all greater than or equal to 0, or we could say 0 through infinity, including 0. And then the last one is actually the exact same as the one we just did. It goes on and on forever to the right and to the left. So my domain is all real numbers, or negative infinity through infinity. My range never goes below 0. So my lowest y value is 0. Everything else is bigger than that. So 0 through infinity. Here's a few more examples if you want to pause the video and try them on your own, and then I'm going to write up the answers. And here are those answers. To tell if a function is linear, linear means line. It would create a line if we were to graph it. And all linear functions can be written in the form y equals mx plus b. So this first function is not linear because we have an x squared term, and that's not a part of y equals mx plus b. So it's not linear. Our answer to that would be no, but we can still evaluate the expression when x equals -4. That just means we're going to plug in -4 into the function and solve. The only thing you have to be careful here is making sure you do order of operations correctly. And for this one, we get that f of -4 equals -1. And another way of saying that is when x is -4, y is -1, or the function value at -4 is -1, or as an ordered pair, that would say -4, -1. That's the point on that function. G of x is linear. It's in the form y equals mx plus b. It can be put in that form where 5 is the slope and 8 is the y-intercept. And if I want to evaluate at -4, we get 5 times -4 plus 8. That's -12. So G of -4, or the output when the input is -4, is -12. H of x is also linear. It can be put in the form y equals mx plus b. We have an mx, we have a b. We don't have anything other than that. And when we evaluate this at -4, we get, let's see, -4 plus 8 is 4. So we have the ordered pair -4, 4. When we input -4, the value of h is 4. And then the last one is not linear because of the x cubed. We don't want an x cubed. That would be a cubic function. This one up here is a quadratic function. And then when we evaluate this one, we have j of -4 equals -4 minus 1 minus -4 cubed. Make sure when you are substituting -4 for x, you're substituting it in parentheses. So this turns into a minus -4, which is a 64, positive 64. When we combine all that together, we get 59. The last thing we talked about in this lesson is just reviewed real quickly how to graph something that is linear. So if it's in the form y equals mx plus, well, if it's not in the form y equals mx plus b, put it in that form first, because everything linear can be put in that form. And then we graph the y-intercept first. So the number in front of x, that's your slope. The other number, that's your y-intercept. The y-intercept is a point, the slope is not. So graph the y-intercept first, and then use the slope to get your second point. Slope is 2, that's 2 over 1, and so we go up 2 over 1. The next one, the y-intercept is 3. My slope is 2/3, so we go up 2 over 3, or we can go down 2 and to the left 3 because two negatives make a positive. And we want our slope to be positive 2/3, which means from left to right, we want our graph moving up.